Hopefully we're comfortable solving rational equations, since in this section we'll be working with word problems that lead to a rational equation. In this lesson, I will focus on the work rate and distance problems. These are the more difficult of the four types that you will see in this section. You were introduced to these steps earlier. Word problems are not easy. Therefore, take your time. Read the problem as many times as necessary to understand what is going on. You may need to model the problem you are doing with one already done by the author or an instructor. Oftentimes we need to gain familiarity with a certain type of problem. In other words, how we set up a problem and what formula we use depends on what type of problem we are working. This slide is here to provide background for the work rate problems. Work rate problems involve two or more people or machines performing tasks at different rates. When we deal with their rates, assume it to be represented by 1 over the time it takes them to do the task alone. For example, if it takes 4 hours to complete a task, 1 over 4 can be interpreted as the entire task is completed in 4 hours. There's a lot of information on this slide. We will see this all organized in a table format once we get to the work rate problems. Here are the important points. Our formula will be rate times time equals part. The rate we talked about on the previous slide. This will be 1 over the time a person takes doing the task alone. The time will be the time the two people take to do the same chore together. The product or the part will be the part or percentage that one does when they are working together. We will take these two parts or percentages, add them together, set them to 1 to get the equation necessary for us to answer the author's question. Now that I've thrown all of that at you, let's take a look at our first problem. Paul takes 45 minutes to wax his car. John alone takes 30 minutes. How long will it take them working together? Now, it would be nice to have a way to check the reasonableness of our answer once we get there. So here's a question that will help us do that. It will take less than how many minutes working together? Now look at it this way. The fastest person, John, now has a helper. He takes 30 minutes working alone. Now he has a helper. And with the helper, it will take less than the 30 minutes to wax the car. So here we go. We're using a table for the work rate problems. Across the top, your formula, rate times time equals part. The two people go off to the far left, and their information goes across the row. Paul's rate is 1 over 45 since he takes 45 minutes alone. John's rate, 1 over 30 since he takes 30 minutes. Time is defined to be their time together. That's our unknown. Therefore, T goes in both of those spots. Multiply across for the part. Now see part as a percentage, the percent that one does when they work together. Now since John is faster, shouldn't he end up doing more than Paul when they're working together? Now because the parts really represent a percentage, we add them, set them equal to 1, and see the 1 as 100% the task gets completed. We have a rational equation with the least common multiple of 30 and 45, 90. Multiply all terms by 90 to clear the denominator. Multiplying through, canceling denominators, we end up with a solution of 18 minutes. So it takes Paul and John 18 minutes to wax the car working together. And this is definitely faster than what John can do alone. Here's another work rate problem. Always start the work rate problems by setting up the table. This time we're given the time it takes working together, and the individual rates are unknown. So one person takes twice as long as the other person. Therefore, under the rates, one is 1 over x, and the other is 1 over 2x. Time is defined to be the time together. The 8 minutes goes in this position for both people. Multiply across for the part. add the parts, and again, set equal to 1. Now if we want multiplied by x, we would clear the denominators. Remember to multiply all terms by x. It's a common mistake in a problem like this to forget the right-hand side. So here we go. It takes one person 12 minutes, the other person twice as long, 24 minutes. Notice how the time to work together is, again, the shortest time. Let's take a look at a uniform motion problem. Read the problem carefully. We have a situation where there is a boat traveling upstream, against the current, and then downstream, which is with the current. The problem says these two trips will take the same amount of time. This is a very important statement to catch, since it provides the starting point to arrive at the equation to solve this problem. By the way, the formula we are going to need is distance equals rate times time, although we're going to need to rearrange it. The times are the same. We'll come back to that. Our unknown is the speed of the boat in still water. Is the boat ever in still water? No, because it travels against the current and then with the current. So here we go. Use the table to organize the information. Let's start with the rates. When a boater is moving with the current will speed up the boat by how fast the river is flowing. So the rate of the boater, R, the rate in still water, and then +3, adding on the speed of the current. When traveling against, the boat gets slowed down by the current for a speed of then R-3. The times are the same as stated earlier. Distances are given. Now where do we go from here? We'll go back to the statement about times being the same. But first, we work with the formula. If we are going to use this fact, the times are the same, we need to rearrange the formula so that it's solved for t. So when we divide by r, we get that time is distance divided by rate. Now at the bottom of the slide, we replace time with distance over rate. Pulling the distances and the rates from the table, we now have an equation that will allow us to solve for r. We can cross multiply to solve. So after cross multiplying and solving, we get the rate of the boater as he's moving through still water. So the boater travels at 30 miles per hour in still water. So hopefully this gives you a good start in solving these two types of word problems. Thank you.